Hello, my name is Prisha, and today we're going to be learning about coordinate geometry. I'll be covering some of the basic features of a coordinate graph, the distance formula, the midpoint formula, and the four types of movements of points, which are translation, rotation, reflection, and dilation. We'll then go over the things that you're asked to move and end with some examples. Let's get started. Let's start off with a refresher on the basic features of coordinate graphs. The origin is the center point, also known as 0, 0, which is the intersection of both axes. We have an x-axis and a y-axis, which are the scales that measure the distance from the point to the origin. The x-axis measures the horizontal distance, and the y-axis measures the vertical distance. Now, if we look at the entire graph, the x and y-axis form a sort of plus sign that divides the plane into four sections, which we call quadrants. They're all labeled from 1 to 4, starting from the top right and moving counterclockwise, but you'll usually see them as Roman numerals. The first quadrant is where both x and y coordinates are positive. The second is where just the x coordinate is negative. The third is where both coordinates are negative. And the fourth is where just the y-coordinate is negative. This is all important information to keep in mind, as there will be questions that ask you about the quadrant of your final answer, or tell you to manipulate points along the x and y axis, or say the origin as opposed to 0, 0. Don't blow off knowing the basics. Let's say you get a problem on the ACT, SAT, or your test that goes as follows. A puppy starts at -5, 3 and starts running in a straight line. He stops at point 1, -5. What is the total distance that the puppy traveled? If the graph is drawn out, we can see that the line is diagonal, meaning we can't just use the horizontal or vertical distance in between points. But since I know the horizontal and vertical distance in between points, I can turn this into a Pythagorean theorem problem, with the legs being the horizontal and vertical distance, and the hypotenuse being my answer. The horizontal distance is the second x-coordinate minus the first x-coordinate, so that would be 1 minus -5, which would get me 6. And the total vertical distance is the second y-coordinate minus the first y-coordinate, so that would be -5 minus 3, which would give me 8. We're disregarding the negative sign because triangles can't exactly have negative side lengths. So my equation would then be a squared, so a is my hypotenuse again, a squared equals 6 squared plus 8 squared, which would then go to a squared equals 100. That's what 6 squared plus 8 squared equals. And then a would equal 10, which is my answer. If you don't want to go through the hassle of setting the Pythagorean theorem, you can just use the more concise distance formula as written here, which is d equals the square root of the second x-coordinate minus the first x-coordinate squared plus the second y-coordinate minus the first y-coordinate squared. It's easier to do it this way, but it is another formula to memorize, so just pick the way that you think would be faster and easier for you to memorize. Let's say you get another problem that goes as follows. Kelly lives at a house on point -5, 3. Shelley lives at a house on point 1, -5. And Nellie lives at a house that is at the midpoint between Kelly's and Shelley's houses. What are the coordinates of Nellie's house? To find the answer, I like to think of the answer as having an x-coordinate that is the average of the x-coordinates of the endpoints, and a y-coordinate that is the average of the y-coordinates at the endpoints. That means that my x-coordinate would be -5 plus 1 over 2, which would be -2. We're not disregarding the negative sign here because we're trying to find an exact point in the coordinate plane. And my y-coordinate would be 3 plus -5 over 2, which would be -2 over 2 or -1. Therefore, the coordinates of Nellie's house are -2, -1. This is the more intuitive way to think about it, but there's also a formula that you can use to directly plug things into, which is the second x-coordinate plus the first x-coordinate divided by 2, comma, the second y-coordinate minus the first y-coordinate divided by 2. What you use, again, it just depends on what is faster or easier for you to understand and memorize. It's now time to move on to movements. The first type of movement is a translation. It's notated with a T, a subscript of the amount x has to change, which is A, and a subscript of the amount y has to change, which is B, and the original point. The formula is simply adding A to x and B to y, and then you get your final answer. If I wanted to translate -3, 6 using 5 and -2, as seen here, I would simply add 5 to -3 and 6 to -2, which would give me an answer of 2, 4, which I will draw right here. On a side note, if your question does not notate translations this way and instead asks you to move the point to the right, left, up, or down, keep this in mind. Moving to the right means you'd add to the x-coordinate because you'd be going farther on this positive plane. Moving left means you'd subtract from the x-coordinate, meaning that you'd go right here because you're going towards the negative side. Moving up means you'd add to the y-coordinate, that's pretty intuitive, and moving down means you'd subtract from the y-coordinate, also intuitive. The process of finding the answer is then the exact same. The second type of movement is a rotation. There's no specific notation for this, but the thing to keep in mind is the formulas for all types of rotations. If we rotate a point x, y 90 degrees about the origin, we will end up at -yx, which we can prove right here, which is with this point 8, 3. Although I can't really show it to you using the demonstration of putting a clear sheet of acetate and rotating at 90 degrees, we can kind of know the ballpark of where this would end up if we rotated it 90 degrees, which is somewhere here. And that's exactly where this formula points us to. We'd end up at -3, 8. Now, if we wanted to rotate a point x, y 180 degrees around the origin, we'd end up at -x, -y. Again, I can't exactly show you this, but if we rotate it, we'd end up somewhere in this ballpark range, which is exactly where that formula points us to. We'd end up at -8, -3. And finally, to 70 degrees. If we rotated a point xy to 70 degrees, we'd end up at y, -x. And if we rotate this to 70 degrees, we'd end up at 3, -8, which all checks out. Finally, a 360-degree rotation is the easiest. You end up where you started. If you get a measure beyond 360 degrees, you'll want to remember to subtract 360 degrees from the measure until you end up at something less than or equal to 360, after which you can keep using the rules as normal. Also, keep in mind that all these rotations are counterclockwise. This is the default direction, but if a question asks you to rotate clockwise or to a negative value, you're going to just switch the 90 and 270-degree rule and then proceed as normal. You will only be asked to rotate for these degree measures, so don't worry too much about finding rules for other degree measures. Also, remember that these rules only work when rotating about the origin. If you're rotating about another axis, you'll be expected to ballpark the answer rather than get something exact. So again, don't stress if you encounter something like that. At that point, just kind of visually know where you're going. The third type of movement is a reflection. There's only two ways to reflect, across the x-axis and across the y-axis. To reflect across the x-axis, we're going to make our y-coordinate the opposite sign, negative if the original is positive and vice versa. Or we can use this formula, x comma negative y. So in this example, my new point would be 8, negative 3, which makes visual sense. To reflect across the y-axis, we need to make our x-coordinate the opposite sign, or use this formula, negative x, y. In this example, my new point would be negative 8, 3, and that also makes intuitive sense. The fourth type of movement is a dilation. A question will usually tell you the factor of a dilation, or you'll have to figure it out, but all you have to do once you get the factor of dilation is to multiply both the x and y coordinates to end up with your final answer. For example, if my dilation factor here is 0.5 and I have a point 0.83, I'm going to multiply 8 by 0.5 and 3 by 0.5, getting me 4, 1.5. And that's all there is to it. That's all the types of movements. So, what are the things that a question can ask you to move? Well, you can obviously move points. That's what all the formulas mentioned have been catered to. But you can also move shapes or a cluster of points. Just perform the operations required to every point within the shape, or on every vertice. For example, if you're moving a square, sorry for the wonky square, you're going to have to perform the operations to every vertice of the square, every corner. So you're going to have to perform operations to 4 points in total. On a side note, you can perform multiple operations to one point, such as translating and reflecting it, or reflecting it over the x-axis and then over the y-axis. Just make sure to do these operations sequentially to get the best results. Most of the problems with these types of questions usually don't come from not knowing the material, but rather going too fast and missing a step, or like not adding something to a coordinate. These problems aren't too bad, but take your time with them when you can, because it will be worth it and you won't have the chance of making silly mistakes. The next thing that you can move are functions, and they have a whole set of new rules. When you translate left, add the translation factor to x and use it within the function. When you translate right, you're going to subtract the translation factor from x and use it within the function. Moving up and down are pretty intuitive because you're just going to add the translation factor to the entire function or subtract the translation factor to the entire function. But moving right and left can be a little bit counterintuitive, especially from translating right and left from before, because to move left you're actually adding and to move right you're actually subtracting. Now, the next thing is rotating, but we can't actually rotate our function because we would end up with two y coordinates for the same x coordinate. For example, if we rotated our function 90 degrees or 270 degrees, and I'm just going to be rotating a parabolic function because that's a little bit easier too, we'd end up with two y's for the same x in a lot of spots, which means that the function wouldn't be a function anymore. Remember, the definition of a function is that each x has only one y, even though multiple x's can have the same y. Now, to reflect a function, we can reflect a function across the x-axis by simply making the entire function negative, and we can reflect the function across the y-axis by just making the x's negative. So not the entire function, but just the x's within the function. Finally, dilation is the simplest. You're just going to multiply the entire function by the dilation factor. Another thing to keep in mind with function problems is that you might be asked to select a graph that matches a moved function, or you'll be given a graph of a moved function that you have to figure out the formula to. Make sure you can do your problems vice versa to keep yourself for any tricky questions that the ACT, SAT, or your test may throw at you. Lastly, you may be given a line of symmetry problem. There's only two things to keep in mind with these types of problems. One, make sure each half of the shape is a reflection of the other when splitting it down a line of symmetry. So for example, a circle has infinite lines of symmetry because when you split down the center, forgive my split down the center, but you'd have equal halves on each side, and that doesn't matter as long as you put that line so that it divides the circle in half. And the second thing, you don't want to double count lines. So double counting is the easiest way to get these problems wrong, so slow down when you can and double check that you got the amount of lines right. I see a lot of times where people double count when they think, oh, I'm gonna rotate and I'm gonna do lines of symmetry. So I'm gonna do one line here, and then they double count this line by saying, oh, I need another line of symmetry here and another line of symmetry here. That's 4 lines of symmetry, and you don't need 4 lines of symmetry. You just need the top one and the side-to-side one. Now on to the last leg of this presentation, examples. So this first example, so trapezoid ABCD is graphed in the standard XY coordinate plane below. When ABCD is reflected over the y-axis to A prime, B prime, C prime, and D prime, what are the coordinates D? So that means that I could reflect this entire shape over the y-axis, but since we're just trying to find coordinates D prime, I'm just going to reflect this coordinate right here over the y-axis to get my answer. Remember, when you're reflecting over the y-axis, you're going to make the x negative. So you're going to end up with negative 12, 1. So I think the answer to here is F. Okay, the graph y equals f of x is shown below. What could be the graph of y equals f of x minus 4? So for this graph, we have a simple function translation problem. So when we're subtracting 4, that means that we're actually moving to the right, because subtracting means moving to the right and adding means moving to the left. It's that counterintuitive thing again. I always remember it as the opposite of what I would think it would be. So f of x minus 4, that means we're going to be moving to the right. So I got to pick a graph that looks like it's moved to the right. And in that case, I think this graph would be good, because this graph looks like it's translated up, this graph looks like it's translated down, this graph looks like it's translated to the left, and this graph looks like it's been translated down and to the right. So I just want a translation right, because there's no other translations going on here. Okay, on to example 3. The triangle XYZ that is shown below has side lengths x, y, and z inches and is not a right triangle. Let x prime be the image of x when the triangle is reflected across yz. Which of the following is an expression for the perimeter in inches of quadrilateral x prime y x z? So this is actually a pretty interesting problem. So if I'm reflecting x across the plane yz, that means I'd end up with something right here, like x prime. And if I wanted to make it a quadrilateral, I'm just going to connect all the points in the order that it's shown here. So I would connect x prime to y, y to x, x to z, and z back to x prime. So this shape, since we're basically doubling this triangle, it's either going to be a rectangle or parallelogram, which means the top side and this bottom side are going to be the same, and this left side and right side are going to be the same. So that means I can just write y here and z here, because essentially we've made 2 of these same triangles. So if I wanted to find perimeter, I would just add all of this up. There's 2 y's, 2 z's, and if I took out the 2 from that expression, I would end up with k, 2 times y plus z. This is a very interesting problem, actually. I've never really seen anything like this before, but that's the kind of question that the ACT, SAT, or your test likes to throw at you, because it does not test the fact that you've learned all the types of questions that go along with the problems. It tests the fact that you've memorized the approach and kind of the thinking that goes behind these types of problems. So you need to be able to use all your skills on those problems and your common sense in order to get these types of tricky logic problems right. But usually they're very easy once you kind of figure out the logic behind them. Okay, on to example 4. As shown in the standard xy coordinate plane below, point P66 lies on the circle with center 2, 3, and radius 5 coordinate units. What are the coordinates of the image of P after the circle is rotated 90 degrees clockwise about the center of the circle? Okay, so this is actually one of the problems I was talking about, where you're not going to rotate about the origin, you're instead going to rotate about another axis. So with this type of problem, what I'm basically going to do is ballpark my answer. So since I'm rotating 90 degrees clockwise, the way I think about it is I'm going to be drawing new sets of axes. So I draw an axis through what I'm going to be deeming the new origin and my point, and I draw another vertical axis. So that way I'm kind of dividing the circle into 4 quadrants, and it makes it really easy to see where that rotated 90 degrees clockwise point would be. Also, you should note that it's rotating 90 degrees clockwise, not counterclockwise. So we really need to make sure that's either underlined or boxed or like starred, because this is the kind of thing that trips people up. If you don't read clockwise, you're going to rotate the opposite direction and you're not going to get the correct answer. So if we rotate 90 degrees clockwise, it seems like I'm going to get an answer of somewhere here. So let's look through these answers and see which seems right. So 2, 3 is definitely not right because that's the center of the circle. 3, 2, that would be about here. That doesn't seem right. Why would it go closer to the center of the circle? We're rotating around like that circle. 5, -1, that actually does seem about right. That's pretty much exactly where my point is. So I'm just going to put a line by it and keep it in mind. 6, 0. So 6, 0 is where that circle kind of intersects the x-axis, but I don't think that's going to be the point where I've rotated this 90 degrees, because if I just ballpark, I can see that P would rotate a little bit more. I don't think that this is an exact quarter of a circle. So D is kind of, I'm more confident about C than I am about D, so I'm going to kind of X that out. And E is 7, 3. Well, we know that this is kind of in the negative plane. It looks pretty close to the negative plane, so I don't think we'd be all the way up at 7, 3. That seems way too short to be a quarter. So I think my best answer here is C. So you see, you don't need to be very exact when you look at these problems. You need to be able to ballpark and kind of get a sense for where things would be. So if you're not exactly sure about what the formula for like a rotation or for a flip is, the best thing to do there is ballpark. Okay, so example 5. The figure below shows a design of a circular stained glass panel on display at Hopewell's Antique Shop. Seams separate the pieces of the panel. All red triangular pieces shown are congruent and have a common vertex with each adjoining triangular piece. The 2 squares shown are inscribed in the circle, and the diameter of the panel is 2 feet. So all this information that like the diameter of the panel is 2 feet and such, that's kind of thrown out of the window in a lines of symmetry question. I don't really need to know the exact dimensions of each piece. Rather, I need to know, I just need to go through and mark all the lines. So let's go through this. So the first kind of line that I'm seeing is one where I hit between the triangles and I hit between the triangles here. That way we'd end up with 4 triangles here, 4 triangles here, and a half circle on each side. So I'm going to make one line like that, one line like that. Sorry, they're pretty wobbly. One line like that, and one line like that. So that's 4 total lines. So right now I can eliminate F because I definitely know it's not going to be 2 lines. And now I need to figure out a couple more lines. I don't think this is it, because these triangles are, they're congruent. They look like isosceles triangles. So I would think that I can just split both triangles in half, and I would end up with 3 and 2/2 triangles on one side, and 3 and 2/2 triangles on the other side, and obviously end up with half circle on each side. So I could go through and divide all these triangles. I'm going to spare you my bad line drawing skills. So I'm just going to say that there's going to be 4 more lines. So let me just write down how many lines I have so far. So we have the 4 lines going in between the triangles, 4 lines going through the triangles, and I don't really think that there's any lines left, because though the circle can be like divided into infinitely many sections, I can't divide this into infinitely many sections, because if I divided it where I wasn't perfectly in the center, I'd end up with something that would be not a mirror image of itself. So it wouldn't be a line of symmetry. You always want to think that like you're placing an imaginary mirror on the line you drew, and if that mirror reflects the other side perfectly, that means that there's a line of symmetry there. So I think 4 plus 4, that's all the lines of symmetry I have, which means that my answer would be H. And that's all. Thank you for listening and have a wonderful day.